Entropy, entropy, entropy. What is entropy? Too often we have the overly simplistic definition of entropy, which is the measure of randomness or disorder, the idea that if you leave your toys and a toddler unsupervised in a room, everything is going to get messy. And while that's very true, there's more to entropy than just the decline into a random state. It's more about thinking about all the possibilities there could be for disorder. So when we think about maybe house cleaning, there's the idea of minimalism, which you see in the bottom right-hand corner of this slide, that if you have less stuff, your stuff will not get cluttered and disordered, and therefore you'll have an organized home. You have that type of idea, or the top right-hand corner here where you have everything in its place. Everything has a place and it can go there, and therefore you have more order about the house. Well, I want to introduce a slightly different definition of entropy using these ideas of minimization and order and disorder. And that is the idea of what causes a mess. A mess occurs when an object is not in the place it's supposed to be. So if the object can only be in one place and there's no place else it can go, then you won't have a lot of randomness. And that's the approach of minimalism. If you only have 5 places at which you can put your pillow, then it's going to be in one of those 5 places and there's not going to be it strewn all the way around your room. Whereas if everything could have 500 locations upstairs, in your sock drawer, in the laundry basket, outside where the dog took it, there's a lot more options for randomness and disorder. And so entropy, instead of it just simply being an idea or a concept, we're going to talk about probability and how probability plays a role in deciding whether or not you're going to have an increase in entropy or a decrease in entropy. So the idea behind entropy is we're talking about the order in the universe and the idea that nature tends toward the states that have the highest probability of existing. The more probabilities that exist, the more entropy you're going to have because the more chance for disorder. Now, what in the world does this mean? Well, let's look at this card example. If I spread out these cards in front of you and I ask you, find the pattern. Now, most of you could quickly figure out the pattern. They are ordered ace through king. We got spades, then diamonds, then clovers, then hearts. Clovers, I call them clovers. Clubs, that's the real name. But the idea is you've got a pattern here. Well, if I take that same deck of cards and I throw them up in the air, allowing them to fall wherever they want and wherever they may lie, you know they're not going to land in order. That's just not the way it works. But why do they get all scattered and disordered? It's because there were many different places that each card could take within the deck of 52. And so because of that, they didn't just have one place where they could lie, there were lots of places. And so you get, because you have a higher probability of number of places that card could lie, you have more disorder. Whereas if I only had 1 or 2 types of order, like this nice fake trick deck that is entirely made out of aces, if I select any ace and move it around and switch its position with another ace, I didn't change the order too much. I did in actuality, but it doesn't appear that I changed it. And so it doesn't look like there's many probabilities as to all the different ways that the permutations is the mathematical idea at which the individual cards could exist. And so the idea behind that is if you have fewer probabilities, you have less disordered. And in this case, that's entropy. And so we're going to relate the terms probabilities to entropy and think about how an entropic increase is going to be the idea of more disorder, but it also means more probable positions or places or states exist. So let's say we have a tube like this. Which of these 2 ways do you think the gas is going to exist? So if I have a piece of glassware that's 2 circular spherical ends with a channel in the middle, and then I have a gas inside of it, is the gas going to randomly disperse like you see on the one side, or are all of them going to move to one side of the flask, leaving the other side completely empty and vacant? It's going to exist like our first picture here. But why? Why will it end up like that? We know gases disperse and fill up their containers, but the driving force behind that is entropy. We just didn't necessarily know or understand why it is. And the reason behind that is something called microstates. It was just a way of us trying to categorize probabilities in our brain so we can make sense of this concept. All right, so same flasks here, but now let's minimize, let's simplify it and say we only have 4 molecules or atoms. How can those 4 atoms exist inside of this container? They could exist with all 4 of them on one side, like in arrangement 1, or all 4 of them on the right side, like in arrangement 5. Or they could exist with 3 and 1 or 2 and 2. So all of these different ways play a role. And so you might think, oh, well, based on this, it looks like arrangement 1 and 5 are equally probable. But that's not the case. Why? Because you can treat each individual atom or molecule as a specific entity. And so when we draw out the probabilities for them, we'll find that there's actually more ways they can orient themselves. What do I mean by that? Look at arrangement 2. So arrangement 2 said there's 3 atoms or molecules on one side of the flask and 1 on the other. But is that 1 the A molecule, the B, the C, or the D? Depending on which specific atom is all by itself, changes the states or the microstate within that arrangement. And so there's 4 different microstates that can have the arrangement that we see in our arrangement 2. There's 6 that have arrangement 3, 4, arrangement 4, and 1 for arrangement 1 and 5. And so if you'll notice, our thing that has the most microstates is arrangement 3. And that's the equal dispersion of the different atoms or molecules on both sides of the container. And so that helps support the idea that whichever arrangement has the most number of microstates or probabilities, then that's what's going to exist the most commonly in nature. And so the idea is more probability something has of existing, the more entropy it's going to have, and the more likely we're going to have that state exist. All right, so how does this apply to a lot of different things? So when we talked about the ideal gas law, we had pressure times volume equals moles times your gas constant times your temperature. We're going to use those same main big picture ideas of pressure, volume, moles, and temperature and apply them in looking at different ways that entropy can exist. So what I mean by that is if we look at solid, liquids, or gaseous states, what's different for these? Well, temperatures, movement of molecules, rigidity of the intermolecular forces, all of those things which you've already learned about, but they all play a part in determining which state has the most entropy. So think about a solid. A solid is held rigidly together, so the molecules don't have a lot of ability to move around. And so because of that, there's not a lot of different positions that the molecules can take. So their positional entropy is low. Whereas a gas, man, those molecules are moving around like crazy. Since they're moving around, there's many different places that each atom could exist in, and so there's more probabilities or more different locations the atoms can exist in. That's your messy room that doesn't have order. Whereas the solid, everything has its place. It goes where it's supposed to go. So the disorder in a well-organized room is very low. Whereas a room or a structure that doesn't have a lot of order to it, like a gas, that entropy is very high. And so what we see is that the entropy in a gas is bigger than entropy in a liquid, which is greater than entropy as a solid. And so the most disorder exists in the gaseous phase. And you'll notice the arrow going between the entropy of a gas and entropy of a liquid has 2 little carets on it, and that's because it's so much bigger than a liquid, just because of the larger number of microstates that exist in the gas phase. Okay, so that's temperature, because temperature is going to help you relate gas, solid, liquid, etc. to each other. What about moles? How does moles play a role? Well, look at this structure here. We've got N2, nitrogen, plus 3 hydrogens going to 2 of our ammonia compounds. So on the left side of our reaction arrow, we have our reactants. There are 4 reactants, whereas on the right side, we have our products, and there's only 2. And so because there's more moles on the left side, that is greater entropy, greater places of disorder as compared to the right-hand side. And so this would be an entropic decrease because there's less entropy that's associated with the 2 molecules on the right side of the arrow compared to the 4 molecules on the left. So not only do we need to consider gas, liquid, or a solid, we also need to consider the number of moles that are present as a reactant or as a product in order to help us figure out what happens to our entropy. So when we're looking at entropy, we can look at them using all of these things. So we've got our number of molecules, our volume, our temperature, and our pressure. And so changing any of these things will change our entropy. And so positional probability is associated with number of atoms or molecules, because remember back in this, it's where can all of the pieces take place. And so we have a lot more pieces, and so there's a lot more random positioning that can happen, and so that's more probabilities, which leads to greater entropy. And so that's called positional probability. The next one is volume expansion. If we expand our volume, we're going to increase the number of microstates because we are increasing the number of positions that our individual molecules or atoms can take up within the space. And so increasing volume results in an increase in entropy. Increasing temperature also results in an increase in entropy because increasing temperature increases the energy of the substance. It increases the amount of disorder that can happen. It's like giving your child a bunch of sugar, okay? More disorder happens. So increasing the temperature also can change the phase of the substance, which can affect those intermolecular forces and the rigidity of the system. Increasing temperature, increase in entropy. Decreasing temperature, decrease in entropy. And then the last one, the pressure changes, is the opposite of all the other ones. All the other ones are if you increase moles, increase volume, or increase temperature, that means you're going to increase entropy. Pressure is the opposite. Increase pressure, you're decreasing entropy. But why is that? Well, if you keep the same number of temperature, or the same temperature and the same number of moles, if you lower the pressure, you can only achieve a lower pressure state by increasing the volume. And if you increase the volume, we already saw before, you're going to increase the number of microstates, which increases the entropy. So pressure is the opposite of all of the others. Basically, this is a summary. Increases in entropy are associated with increases in moles, increases in volume, increases in temperature, but a decrease in pressure for all of the reasons we saw on the previous slide. Let's now do some examples. Which of these pairs has the greatest entropy? Solid carbon dioxide or gaseous carbon dioxide? I hope you chose gaseous carbon dioxide because they're not held as rigidly, so there's greater probability and greater entropy. What about nitrogen gas at 1 atmosphere as compared to 1 times 10 to the negative 2 atmospheres? Which one has a greater entropy? The lower pressure has the greater entropy because the lower pressure means larger volume means greater entropy. What about these next two? If I take solid sugar and I dissolve it in water, did I just increase my disorder or decrease it? Well, I increased the number of microstates because I'm now having it in an aqueous substance as opposed to a pile or a lump on my desk, okay? And so I now have more locations or more probabilities that those individual sugar molecules can exist in, and so that's an entropic increase. What about iodine vapor condensing onto a cold surface? Well, what is condensing? Condensing is where you take it from the gas phase and you turn it into a liquid phase. So that's a loss of temperature or a loss of energy, which is equal to an entropic decrease. So that's entropy. Try and think about how entropy is related to both microstates, which is the idea of probabilities, but then also moles, volume, temperature, and pressure.